We are now going to get into some of the derivative rules, and they seem to be easier than the definition of a derivative, but they're not all that easy. So I want to point out that you can always go back to the derivative, the definition of a derivative to do it and find the limits and so forth, or you can use these rules. But these are the rules we're going to work with. So the first rule we're going to work with is what is called the power rule. So let's just say we have a function y equals c, just f of x equals c. I want to find out what its derivative is. So remember, this is the rate of change. I want to find out what that is. So using the definition of limit, the limit definition of that, we're going to have the function minus the function. Well, my function in this case is just a constant and a constant. There is no something to put the x plus h into. There's no something to put the x into. So it's just a constant minus a constant over h. Well, a constant minus a constant would be 0 over h, which is just 0. And the limit of a constant is just 0. Because the limit of 0, I should say, is just 0. It's just the constant itself. So this is the derivative. So the derivative of a constant, f prime of, we'll actually write it a different way. The derivative of a constant the derivative with respect to x of some constant is always just going to be 0. And if you think about the graph of this, so if we look at this graphically, a constant is just a horizontal line. And the slope of every horizontal line is 0. So it makes sense that its derivative would be 0. All right, so now let's look at other more interesting functions. So let's look at the derivative with respect to x of x to the n, where n is some positive integer. Right now we'll just work with positive integers. So let's say n equals 1. So again, you want to think about if n equals 1, it's just x. And the line y equals x looks like this. And slope is just 1. So it makes sense that the derivative of x is just 1. The derivative of x squared turns out to be 2x. The derivative of x cubed, and again, you can see this if you look at the graph of it. Here's x squared. Again, the derivative would be, we're decreasing, so the derivative is negative. Then we're increasing, the derivative is positive. So we're decreasing, so the derivative is negative. We're 0 right there, and then we're increasing again, so the derivative is positive. So you can see why it's going to be just x. The 2 comes from the fact that you'll see when you actually go to prove it. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x to the third. This is known as the power rule. The power rule says the derivative of x to the n is n times x to the n minus 1. Notice all these powers got less by 1. So we brought the power down. Notice the derivative of x cubed was 3, so we brought that power down and then reduced the power by 1. This is for when n is a positive integer. So just as a little precursor, it's actually n can be any number. But right now, we'll just work with positive integers. Which means if it's a positive integer, we can actually prove it. It's really hard to prove it if it's not. So let's go ahead and prove this. So the proof of this, again, the proof is always from the definition. So the definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. My function this time is something to the nth power. So we're going to have something to the nth power minus something to the nth power all over h. The first something is x plus h. The second something is just x. Wonderful. So now we just need to multiply this out. Well, this is where it gets to be a little hairy. Remember, whenever you have x plus h to a power, the first term is always going to be x to that power, so x to the n, plus something. And if you notice when you did this, when you were doing x plus h cubed, would be x cubed plus 3. If it was x plus h to the fourth, it would be x to the fourth plus 4. X plus h to the 5 would be x to the fifth plus 5. So this is always whatever this power is this first term. And then reduce the power by 1 on the x and increase the power by 1 on the h. There was no h, so now there is an h. Then we're going to have something, and we don't know exactly what that number is going to be because it does change. And then you're going to reduce the power on the x by 1 and increase the power on h by 1. And it'll keep this pattern going until we get to where there's going to be something times x and then h to the n minus 1 plus 1 x, where the x is now gone, and it'll just be h to the n. And then minus x to the n. So don't forget, this was just multiplying out the first term, this first x plus h to the n, then we still have this minus x to the n. Then the whole thing is over top of h. All right, so this will be the limit as h goes to 0. Well, the x to the n's cancel. So I have an x to the n here and an x to the n here. They're now gone. And then I've got n x to the n minus 1 times h plus something again, x to the n minus 2 times h squared plus dot, 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 plus x h to the n minus 1 plus h to the n, all over h. Now, the reason I didn't worry about what all these somethings were is because I can now cancel an h because every single term has an h in it. So we're now going to cancel one of the h's in the top. We're going to factor one of the h's out and cancel with the h in the bottom. So when I do that, I get the limit as h goes to 0 of n x to the n minus 1, that h is now gone, plus something x to the n minus 2 times h, plus x h to the n minus 2, because we canceled 1, so there was minus 1, now there's minus 2, plus h to the n minus 1, because we canceled 1. And the reason I didn't worry about all those somethings is because every single term here has an h except the very first one. And when I let h go to 0, all of these will go to 0. So we're left with n x to the n minus 1. And so we now have this general rule. And the general power rule is exactly what we just came up with, but I'm now saying it's general because now n can be any real number. I only let it be an integer so I could prove it. We can actually prove it for any real number, but we need a little bit more technique to do that, so we'll do that later. But I wanted to show you kind of what the definition was and how to solve it, how to prove it. All right, so now we're going to use it. So let's find the derivative with respect to x of x to the 8. Well, notice on each one of these, you bring the power down, and then you subtract 1 from the power. So it'd be 8 x to the 7th. Even x to the 5,000, bring the power down, subtract 1 from the power. So that'd be 499. X to the 16th, bring the power down. Now, this is one way to write the derivative, is the derivative with respect to x. This is another way. We have y of equals t to the 16th, and then y prime would be 16 t to the 15th. Bring the power down, subtract 1 from the power. And then another way to write it is we don't always have to use t and x's, we can use anything. So here's the derivative with respect to r of r squared. Again, bring the power down and then subtract 1 from the power, but 2 minus 1 is 1. Now, since it's any one we can actually go ahead and do the derivatives of something like this. So I'm actually going to erase this for a moment. I'm going to start again so you can see how this comes about. I personally, you've been taught in the past that we don't like negative exponents and we don't like fractional exponents. But I actually like negative exponents, especially when we're doing derivatives. We want to actually make things into negative exponents. So we're actually going to take this and make this into a negative exponent. So remember, if it's in the bottom, to bring it to the top, it becomes a -4. So bring that up to the top. Then same rule, bring the power down and subtract 1 from the power. And -4 minus 1 is -5. You can leave it just like this. In fact, I like to because I'm probably going to do other things to it later, and I don't need to get rid of negative exponents. So negative exponents are fine. We like those. Same thing, I don't like radicals. They're not much fun. I'd rather write them in rational exponents. So remember, the 3 is your numerator because it's on the inside. The 5, because it's your index, is your denominator. So the 5th root of x cubed becomes x to the 3/5. Then we bring the power down, and I forgot my derivative symbol. So we bring the power down, and then we subtract 1 from the power. So 3/5 minus 1 would be 3/5 minus 5/5, which is negative 2/5. That's fine and dandy to do these little ones, but we can do more involved things. We can actually have something times your function. And so if I have f as c as a constant and f as a differentiable function, then I can actually take the derivative of c times f of x. That c can come out, and then I've got the derivative of your function. So that constant can come out and just comes out to the front. And the proof of this would be, again, using my definitions. Limit as h goes to 0 of c, my function is c times my function of x plus h minus c times my function of x all over h. And one of the things I notice is both of these terms have a c in them. So we can take that c out. So f of x plus h minus f of x all over h. Now, limit laws, remember there's a limit law that says the limit of a constant times something, that constant come out front. So I'm going to bring that constant out front, and I've got the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, this is the derivative. That's the definition of the derivative. So this would be c times the derivative of my function. So I've just proven it. We can also do sums or differences. So if f and g are both differentiable functions, I can actually add the two functions together. If I take the derivative of that addition, it's just the derivative of the first plus the derivative of the second. Same thing with subtraction. I can subtract the two, same idea, derivative of the first minus the derivative of the second. And I can use those to help me find other derivatives. So let's find this derivative. I'm going to do it the long way. I do want to point out that you don't need to do it this way, but I'm going to do it the long way just so you can see. This is a derivative of a sum and difference, so I can use the rule I just had that says I can take these and do the derivative of each individual piece, added together, or subtracted together. So all I'm doing is using the sum and difference rules that allow me to take these apart and write them as separate derivatives. Now I can use the constant multiple rule that says I can bring those constants out in front. So I'm going to bring all the constants out front. Now I can do all these derivatives. So now I'll find all of these derivatives, and all of these derivatives will equal, well, let's see, the derivative of x to the 5th means, again, I bring the power down, subtract 1 from the power. Notice, by the way, that this 5 was out front, 5 times that, so 5 is times whatever that derivative is. So I left it as 5 times 5x to the 4th. Then it'd be minus 3 times, bring the power down, subtract 1 from the power. Bring the power down, and subtract 1 from the power. Bring the power down, subtract 1 from the power. The derivative of x, remember, is just 1, And the derivative of 8 is just 0, it's a constant. Now I can multiply everything together. So now I have 5 times 5, which is 25, x to the 4th, minus 12x cubed, plus 21x squared, plus 16x minus 6. This is the long way. By the way, I almost never do this in the future. Normally I just start at the beginning and multiply and take derivatives as I go. So 5x to the 5th would be 25x to the 4th. Then this would have been 3x to the 4th would be 12x cubed. 7x cubed would be 21x squared. 8x squared would be 16x. And then 6x would be minus 6. And then plus the derivative of 8, which is 0. So normally I don't do all these intermediate steps. I just wanted to show you what we were doing. But normally I go straight to the end. So let's go straight to the end. Let's find the equation of a tangent line to this curve at this point. So remember, the equation of a tangent line is y minus y1 is equal to the slope times x minus x1. But when we're doing tangent lines, y1 is the y evaluated at the x value. The slope is the derivative of y with respect to x evaluated at the x value, and then x minus x1. So let's go ahead and find that. Let's find this derivative. So the first thing we need to find is the derivative of y with respect to x. Then we evaluate it. So first you find the derivative, then you evaluate it. So 3x cubed, bring the power down. 3 times 3 is 9. So 9x squared plus 7 times 2 is 14. X minus, now this one I'll write out, minus 1/2 times 2/3 x to the minus 1/3. Again, 2/3 minus 1, 2/3 minus 3/3 is negative 1/3. And I wrote it that way just because sometimes we have trouble with fractions. So I just want to make sure you saw what's happening. I bring the power down, then I multiply. So I know that my derivative is 9x squared plus 14x minus 1/3 x to the negative 1/3. However, that's not my slope. My slope is the derivative evaluated at my x value. So evaluated at x equals 1. So it'll be 9 times 1 squared plus 14 times 1 minus 1/3 times 1 to the negative 1/3. So I get to find out what all that is. And I most likely will use a calculator because I don't like adding fractions if I don't have to. And we have calculators now that will do this for us. So 9 plus 14 minus 1/3. And that answer is 68/3. So that's my slope. My y evaluated at 1, by the way, just in case you forgot you had to do that. Remember, my y equation is 3x cubed plus 7x squared minus 1/2 x to the 2/3. So I need to do that. I need to evaluate that at 1. So 3 times 1 cubed plus 7 times 1 squared minus 1/2 times 1 to the negative, to the 2/3, sorry. Make sure I wrote that right. So 3x cubed plus 7x squared minus 1/2 x to the negative 2/3. So again, I'm going to let my calculator tell me what that is. And my calculator tells me that's 19/2. All right, so now I can find the equation of my tangent line. The equation of my tangent line would be y minus my 19/2. My slope, we came up to be 68/3. And that slope should always be a number, don't forget. And then x minus 1, because my x1 was 1. So then that's mine, y equals negative 11/3, 68, I'm sorry, 11/2, 68/3 x minus 68/3. Add 11, it's 19/2 to both sides. And find out what that is equal to. Again, use your calculator for that. So y is equal to 68 thirds x, and then 68 thirds, negative 68 thirds, plus 19 halves is negative 79.6. So there's the equation of your tangent line. Let's say we have the position function is this function 12t cubed plus 3t squared plus 8t plus 4, and that's what s of t is equal to. I want to find the velocity and the acceleration. Remember, the velocity is the derivative of the position. So all we have to do is find the derivative of this. So we're going to bring the power down. So 12 times 3, that's 36t squared. 3 times 2, that's going to be 6t plus 8. Once we have that derivative, we can then find the acceleration, because remember the acceleration is the derivative of the velocity, and it's the second derivative of the position. So we're going to take the derivative of this function. That will give me 2 times 36 is 72t minus 6. And there's your velocity. I'm sorry, there's your acceleration. So there's your velocity, there's your acceleration function. One thing I want to mention is these rule I've been using is the power functions. Power functions are where you have x to a power. This is not a power function. This is an exponential function where you have a base and the power is the x. So make sure you pay attention to the fact that these are different. This is not bring the power down and we subtract 1 from the power. This is a totally different rule. I'm going to sort of derive the rule. We're not going to do the whole thing, but we're going to sort of derive it. Remember, the definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. So this would be the limit as h goes to 0 of, sorry, a, not 2, a to the something minus a to the something. So remember, our function is being subtracted in this all over h. In this first something is x plus h. And the second something is just x. All right, so now what do we have? We have, again, the limit, because we haven't done it yet. A to the x plus h is a to the x times a to the h minus a to the x all over h. Notice both these have an a to the x in it, so I can pull it out. A to the h minus 1 all over h. That a to the x does not involve the limit, doesn't involve h at all, so I can pull it out of the limit, because in the limit's mind, it's a constant. So I'm pulling it out. So I have a to the h minus 1 over h, and I want to find that limit as h goes to 0, and that's where I stop. And I'm like, I don't know what that is. So what we have to do right now, we will be able to find out what it is in a little bit, but right now we have to find this numerically. All right, so we can't actually find it right now. We'll have to find it later, but right now you're gonna have to find it numerically. And what we mean by that is if you actually know what your A is, you can go find that. So let's take an example. Let's say A is 2, and we want to find the derivative of 2 to the x, which would be the limit as h goes to 0, of 2 to the x plus h minus 2 to the x all over h. And so again, that would be the limit as h goes to 0 of 2 to the x, 2 to the h minus 1 all over h. So I skipped a little bit of a step here, but I think you've seen this enough times. The 2 to the x can come out. And then we would find out what this 2 to the h minus 1 over h is. What I mean by numerically is I would actually make up a table of values where I have h values and 2 to the h minus 1 over h. I'd let h get closer and closer to 0. So I do 0.1, 0.01, 0.001, and so forth. Go on either side, so negative 0.1, negative 0.01, negative 0.001. Find out what that is and find out what this is. What I find out is it's roughly equal to 0.69. So it's approximately equal to 0.693. Again, just by letting h get smaller and smaller and smaller and find out what this limit's equal to. We can do the exact same thing here. Let's do with 3. I'll do the exact same process. I won't go through all the steps because we've done these enough times, but the same idea. This would be the limit as h goes to 0 of 3 to the x plus h minus 3 to the x all over h. And then same idea, pull out what's common. You can see you're going to get a 3 to the x come out. And the limit as h goes to 0 of 3 to the h minus 1 over h. Again, numerically, I would set up a numerical thing and find out what that is approximately. I find approximately that that's equal to 1.097. So approximately, that's what that would equal. And I realized I don't have my 2 to the x here, so I'm going to put that back in here. So either that limit is equal to that, equal to, in this case, when it was 2 to the x, it was 0.693, 2 to the x, so don't forget that 2 to the x is there still. So we're just finding this limit. This limit's approximately 0.693 times 2 to the x. Do the exact same thing. This would be approximately 1.097, 3 to the x. Well, one thing we notice is that somewhere between these two, there's some function where that value right in front of there is exactly 1. I know that because this number is less than 1, and this number is bigger than 1. So there must be some number, some base that I could use where this is exactly equal to 1. And if you haven't guessed it yet, that's the number e. So e is a number such that that limit is exactly equal to 1, which means the derivative of e to the x is exactly equal to e to the x. It's the only function in the world whose derivative is itself. It's my favorite function because its derivative is in fact itself. So let's just do a quick another derivative. Let's find the derivative of this function e to the x minus 7x to the 4th. So the derivative of e to the x is e to the x, just what we talked about. Again, it's not a power function, so you don't use the power rule. It's an exponential function, and the derivative of e to the x is just e to the x. Then minus, now we use the power rule because we've got x to a power. So bring the power down and subtract 1 from the power. And there's your derivative.